Hey everyone, and welcome. Today, we are going on a journey into one of the most powerful and honestly beautiful areas of mathematics. We're going to see how taking a problem and shifting it into a whole new dimension, the complex plane, can take something that looks totally unsolvable and turn it into something, well, kind of simple. Let's dive in.
So here it is. This is our mountain to climb today. Now just look at that thing. If you try to attack this integral with the tools from a standard calculus class, you are going to have a bad time. A very, very long and frustrating time. But what if there's a better way? What if we don't have to go through the problem, but can find a clever path around it?
You see, the big secret here isn't about working harder, it's about thinking differently. We're going to lift this entire problem off the familiar one-dimensional number line and drop it right into the rich, two-dimensional world of the complex plane. And that single shift in perspective, well, it changes everything.
So how do we actually do this? Well, mathematicians came up with this brilliant little translation guide. We make a key substitution. We say z is equal to e to the I theta. Now what this does is it takes our integral, which runs from 0 to 2 pi, and turns it into a journey around a circle with a radius of 1 centered at the origin of our new complex plane. With these other substitutions, our scary-looking integral morphs into what's called a contour integral. We're no longer integrating along a line, we're integrating along a loop. It's a whole new game, and it's a game we can actually win.
Okay, so now that we're in this new complex world, something really fascinating happens. The actual path we take around that circle, it's not the most important part anymore. The real secret, the key to the whole puzzle, is hidden at a few special points that are inside our circle.
These special points have a name. They're called singularities. Think of them like glitches in the matrix or mathematical hotspots. They are the exact locations where our function just isn't well behaved. Maybe it shoots off to infinity or does something else chaotic. And here's the crazy part. It turns out these are the only points that matter. They hold all the information we need.
And, not all singularities are created equal. They come in a few different flavors. You've got your removable kind, which is like a tiny little pothole in the road that you can just pave over. Then you have a pole, and that's a serious one. That's where the function's value just blows up to infinity. And then there are essential singularities, which are just pure, wild chaos. Figuring out which kind we're dealing with is absolutely crucial.
All right, let's get back to our problem. Once we do that translation into the z variable, we can hunt for its singularities. And it turns out there are 3 of them. We have a pretty intense one, a pole of order 3, sitting right at the center, at z equals 0. Then we have 2 simpler poles, one at z equals a half, and another at z equals 2. The big question now is, what do we do with them?
Well, our first tool comes from a legendary mathematician, Augustin-Louis Cauchy. He came up with a formula that is just an incredible shortcut for solving some of these integrals. But there's a catch. It only works in certain situations.
Now this is where the magic really starts. Cauchy's integral formula basically says, hey, forget about doing the whole integral. If you have a nice function and a single special point a inside your loop, the answer is just 2 pi I times whatever the function's value is at that one point. It's not an approximation, that's the exact answer. It's a total game changer.
But remember I said there was a catch? Cauchy's formula is perfect if you have exactly one simple singularity to deal with. And our problem is a bit messier. Remember our circular path? It encloses 2 of our singularities, the one at z equals 0 and the one at z equals a half. The pole at z equals 2 is outside the circle, so we can just ignore it, which is nice. But 2 is more than 1, and one of them is complex. So Cauchy's formula, as amazing as it is, just isn't powerful enough for this job. We need to level up.
And that brings us to the main event. This is the ultimate weapon in our arsenal for complex integration. It's called the Residue Theorem, and it's the tool that lets us handle multiple and even more complicated singularities all at once.
The key idea behind this theorem is a concept called the residue. For every single singularity, we can calculate one special number. And this number, the residue, miraculously packs in all the essential information about how the function behaves right around that glitchy point. You can almost think of it as the power level of that singularity.
And the theorem itself? It is just beautiful in its simplicity. The residue theorem says that the value of that entire complicated integral around the loop is just 2 pi I times the sum of the power levels of all the singularities you found inside. That's it. It takes this huge abstract problem and boils it down to a simple process. Find the points, calculate the residues, and add them up.
Okay,
The moment has arrived. We have our problem. We've translated it into a new world. We've found the special points that matter. And now we have our ultimate tool, the residue theorem. It's time to put it all together and finally crack the code of that integral we started with.
So, the path forward is suddenly crystal clear. We already know our two important singularities are at z equals 0 and z equals 1/2. So, our to-do list is short. Calculate the residue for the point at 0. Calculate the residue for the point at 1/2. Add those two numbers together, and we are pretty much done.
All right, first up, the singularity at z equals 1/2. Now there's a specific formula for finding the residue of a simple pole like this. We don't need to get into the weeds, but once you plug in the numbers from our function, you find out its power level is -65/24.
Next, we tackle that more complicated pole sitting at z equals 0. The formula for this one is a little more involved. It actually requires a bit of calculus to find, but the process works just the same. And it tells us that the residue at this point is 21/8.
Now for the crucial step. According to the theorem, we just need to add these two numbers together. We take our -65/24 and we add 21/8, which is the same as 63/24. And that gives us a nice clean sum of -2/24, which simplifies to -1/12. This one little number captures the combined influence of both our singularities. And now, for the grand finale. We take that sum of residues, -1/12, and we plug it into the residue theorem. We multiply it by 2πi, account for a constant from our original substitution, and the math just beautifully simplifies. That intimidating beast of an integral from the very beginning boils down to this single elegant answer, π/12. Problem solved.
But what's really incredible is that this whole process, it's just the tip of the iceberg. These ideas of singularities and residues aren't just some clever trick for solving hard integrals. They actually open up a whole new universe for understanding how functions work, with applications in everything from electrical engineering to fluid dynamics and even quantum physics.
It turns out that if you know where a function's special points are, you know almost everything important about that function. It's one of the most fundamental ideas in all of complex analysis. In fact, let me show you just one more quick example of how powerful this is.
This is something called the maximum modulus principle. And what it says is that for any well-behaved complex function, its biggest value can never ever be found somewhere in the middle of a region. It has to be on the edge, on the boundary. It's like a perfectly stretched drumskin. The highest point is never in the center, it's always on the rim. It proves, yet again, that in the complex plane, all the important action happens at the edges and at those special points. And that really just leaves us with a pretty profound idea to think about. This whole journey was about learning where to look, not at the infinite, endless points along a path, but at just a few very special points hidden inside. It really makes you wonder, doesn't it? What other huge mysteries out there can be solved if only we know the right place to look? Thanks for watching.